This is pre-calculus notes on section 1.2, recursively defined sequence. I'm going to put that title up here. And that's the beginning of your second set of notes in section 1.2. When we left off on the previous set of notes, we got this list of ordered pairs for the sequence we had been examining. So if we have a list of ordered pairs, we should be able to graph those ordered pairs and to show a graphical representation of this sequence, okay? And so that's what you see here. I've already graphed the ordered pairs for you. Here they are, just to make sure that they're showing up dark enough for you to see. Okay. And here we've got a linear graph. Okay, they do line up. They will not always, and when we get to other sections in this chapter, we'll discuss when are they linear and when are they not. I'd like to point out what is the meaning of the word discrete, okay? Discrete in math means countable and non-continuous. If these points were connected in a line, they would be continuous. These are not connected, and the reason why is because we're making a list. There is no term in between 0 and 1. There is no term in between the first and second term. There is no term in between the second and third term. And so you cannot connect these points. This is a discrete list, okay? And so when you're asked to graph a sequence, do not connect them. All right, moving on. Recursively defined sequence. Okay, well, what does it mean that a sequence can be recursively defined? That means there is a method of determining that the nth term by using the term that precedes it. Okay? There are 3 steps to defining a sequence recursively. You have to describe a known term in the sequence. That's usually the first term. You have to use an algebraic expression to define the nth term recursively, and we'll explain more about how to do that. And you have to describe the domain for which the step 2 is valid, okay? Make sure that this is in your notes. Pause the video to get it all in your notes. I'm going to move forward to the first problem. Define the sequence recursively and graph it, okay? So here what I've got to do, 3 steps. I have to first state a term. We're going to state the first term, u sub 1. Okay, that's step 1, state the first term. All right, the next step is to
Vince Luciano, 2534. Vince Luciano, 2534.
The next step is to make an equation for every term that comes after that, for the nth term. So I'm going to put a comma, u sub n, okay? Now, we're always going to relate the nth term to the term that comes before it. The term that comes before it is u sub n minus 1. But I probably should have taken a moment to examine what was happening with this sequence before I started writing the equation. So here I've got 1/4, then to 1/2, then to 1, 2, and 4. So each of these is being doubled. It's being multiplied by 2 to get to the next term. Okay? 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. So to get the next term, you multiply by 2. All right, so I'm going to take u sub n minus 1, and I'm going to multiply that by 2. Okay, that's my recursively defined equation. U sub n minus 1 again means the term that comes before u sub n. Step 3 is to state the domain. So I'm going to put a comma. In other words, which term numbers can you use this function for? You almost always say, almost always, n is greater than or equal to 2. And why is that? Because we're starting with the first term, okay? So if I'm taking a formula that is based on the previous term, you have to have a starting point. Since the starting point is the first term, then the formula is good for every term that comes after that. Since the first term is the number 1 term and is greater than or equal to 2. All right, here I have that same exact function, but I put a little graph paper so that we could take a look at what this looks like in a graph. So the first term, here, this would be in ordered pairs of 1, 2, 3, 4, 5. So the first term has an x coordinate of 1 and a y coordinate of 1/4. The second term has an x coordinate of 2 and a y coordinate of 1/2. That's in between 0 and 1. The third term has an x coordinate of 3 and a y coordinate of 1. And then I've got 4, 2, 5, 4. What would happen if I would double 4? I'd get 8. So how about 6, 8? Okay. Is this linear? It is not. I answered the question for you. It is not linear. And so I said we would see examples of some sequences that are linear and some are not. And again, we'll discuss that more. When are they linear and when are they not as we go forward with the rest of the chapter. Let's see, do I have something else? All right, so here I have another sequence. It'd be a really good exercise to try and pause this and see if you could define this sequence recursively all by yourselves. Again, 3 steps to that. You have to state the first term. You have to state a formula relating u sub n to u sub n minus 1. And then you have to state the domain. If you want to give this a pause, do that. I'm going to go ahead and show what this looks like defined recursively. Okay, so I'm going to state my first term. My first term is -6, so it should say u sub 1 is -6. I want to state the nth term based on the term that comes before it. So I'm going to base it on u sub n minus 1. Now here it looks as though I'm adding 2 every time. So I'm going to say u sub n is equal to u sub n minus 1 plus 2, because each new term is found by taking the previous term and adding 2. And what's the domain? Well, since I started with the first term, the domain is everything greater than or equal to 2. That should say 2. If you ever start with something other than the first term, then your domain might be different, okay? All right, so that's it for the second video in section 1.2, recursively defined sequence.